All right, so let's get down to business. Today we are very excited to bring to you a presentation from the newest member of the U of A Geotechnical faculty, Dr. Albert Yu. In 2011, Dr. Liu received an MEng degree in civil engineering at the University of Bristol in the United Kingdom. He then caught a flight over the pond and received an MSc degree in computational science and engineering in 2016, and a joint MSc and PhD degree, computational science and civil engineering in 2019, all from the Georgia Institute of Technology. A core focus of Dr. Liu's research is the study and analysis of natural and human-induced disasters. His research is centered on the development of more resilient, intelligent, and sustainable civil engineering solutions by analyzing and mitigating landslides, as well as evaluating and improving the design and performance of resilient infrastructures for post-disaster mitigation and community reconstruction. He's also served as a recorder for the Geotechnical Extreme Events Reconnaissance Association, which is an NSF-sponsored organization that helps respond to natural and man-made disasters worldwide. Please join me in welcoming Dr. Albert Yu.
All right, hello everyone. My name is Albert. This is really my first geo seminar that I get a chance to interact with you all. I just arrived here at the end of August, so this is my first month here in Edmonton. Still my first month in Edmonton, so very excited to be here. Today I'm just going to be talking a little bit about the effect of structure on the mechanical behavior of loess and how that might affect the failure mechanism of flow slide in general in cemented soils or soils with very porous structures. In that sense, fabric for the particle arrangement. So in today's talk, I'll be starting with a little bit of an introduction on what loess hazards about. And also we're going to be talking a little bit more focusing on the loess flow slide and starting with field investigation. And then we're going to move to the laboratory scale on the mechanical behavior. And then we're going to move to the physical modeling scale on how the flow slide actually get initiated or the failure mechanism deformation process of the flow slide. And we're gonna digress a little bit, just talk about the visualization. We have a bit of fun just to, you can play around a little bit on your screen with your phone. We will talk about that later and we will conclude and then the presentation. So start with the material first. So the loess has been around on the planet for a very long time. Young in geological sense, but still a very long time. So we've not in short of loess-related hazards. For example, the very famous Teton Dam back in 1975, it was built in 1975, failed a year later in June 1976, when the reservoir is being filled for the first time. And so in this particular case, as you can see from the, let me bring out the laser pointer. And so here you can see from this particular case, this dam, the core material in this dam was loess. So it was compacted loess as the core, and it collapsed and get washed out, and it eventually resulted in the failure of the dam. As you can see this from this sequence of images moving from around 10:30 a.m. on that morning, and then about before 12, and you can see the major collapse and failure has occurred for the dam. And as a material, loess is not the only responsible party for this failure. And the dam was actually built upon a fissured rhyolite foundation. So the water in the reservoir enters through the cracks, enters through into the core of the dam, and then caused the failure of the compacted soil. And the image on your lower slides is the Loess landslide, perhaps one of the most famous landslide events that occurred early in the 80s in China, where this rapid moving landslide actually wiped out almost the entire village that buried more than 500 houses in that village and killed 237 people. So in this particular presentation today, we're going to be focusing on this flow-like behavior or flow-like movement of loess landslides. And so in the 2014 update of the advanced original landslide classification system, the late Professor Hunter did a upgrade here and categorized the flow-like landslide into its own class. And in that class, it provided a lot of type of for that particular type of landslide, which is the flow-like landslide. So, but they did not provide a definition for flow-like landslide in general, but he did provide a definition for each subtypes. So if we combine the subtypes, and we can loosely define or describe flow-like landslide as rapid to extremely rapid flow-like movement of granular material at dry to saturated states that can occur on land or underwater. And so perhaps this image is no stranger to many of here in this sitting here in this presentation. This is the CCTV camera that capturing the moment of the failure of the Bernardino Dam which occurred in January 2019. We see from this image, this is really a phenomenal video because it really showcased the two key characters of a flow-like landslide, which are the rapid deformation and movement, as well as the long run out and far-reaching impact that you can see from this video here. So moving on, let's talk about the Loess flow slide. And we're first going to talk about the material a little bit, and then we talk about the field investigation. So here is the general distribution of Loess on this planet. So Loess covers about 10 to 15% of the land area on Earth, and it contains mainly silt-sized particles that bonded by different cementation agents, such as salt, water film, carbonate, or clay. Salt is the most common cementation agent. And actually, researchers at this point are still not unanimous about the origins of the interparticle bonds. Here, just before I point it out, before I move on, I want to point out, actually, here in Canada, we're lucky. We don't really have this kind of problems. But as you can see in the in Asia, in Middle East, and in Europe, and as well as in the US, we have a lot of this loss coverage on the usually on the surface level or on the overlying layers. So here's some just general characters of the material. So it's problematic, especially upon wetting, because of its metastable structure. It's highly porous and bonded by the cementation agents, the particles. So when the decementation process occurs, the particle going to rearrange itself. We usually call that process collapse. And so for this particular type of loess, which is the Chinese loess, it's a windblow deposit that with increasing fines content moving away from the source material. And so therefore they are termed clayey loess and silty loess. And you can see here, clayey, silty, and sandy loess. But in general, as you can see from your grain size distribution on your right, they're still predominantly silt-sized material. And from the SEM images on your very right, you can see this representative cases where you have the particles, the structure, the particles bonded by the salt bridges here, and then you can zoom in a little bit and see the salt here. So for the study area, we have this is showing the location of the study area in China. This is a terrace, a loess terrace, with a rather simple geological profile. You have the overlaying loess, you have the impermeable clay layer below that, and you have the gravel, and you have the bedrock. And here you have the irrigation problem, and it started in 1968 because of the human resettlement. And we have observed or reported more than 200 loess landslides on that terrace since 1968. At this point, the groundwater is sort of increasing at 0.2 meter per year, and they're causing a slope retreat or depletion of the slope surface at a striking rate of 3% per year, at least between 2015 and 17. So imagine the land, we're losing the surface of this terrace by 3% per year. And also interesting is in the past, the flow slides in loess usually occurred predominantly in section 5, which is S5 here, and section 7. But now these days we see an increasing amount of flow slides that are occurring in section 2. So it's actually at this point, the section 2 become a bit of a hotspot for flow slides in loess in this study area. So we look at the groundwater level, and here the groundwater level, the data is combined by a 25 ERT surveys along covering the entire surface area of the terrace, and also the monitoring well, 6 monitoring wells located at different locations on the terrace. And you can see by combining and estimating the groundwater level, you can see here, the blue means high groundwater level and the red means low groundwater level. But still, the groundwater level is high in this terrace, and notwithstanding the dynamics of the surface seepage along the margin of the terrace, what we find here is it's very interesting that we have a very high groundwater level here in this region. And the reason for that is what we find here is actually has something to do with the irrigation intensity. And that has something to do with the crop fields, depending on where they're located. So you see the blue regions here, and they are vegetables. And the green regions here, and they are actually wheat crops. So those fields demands the highest groundwater intensity, ergo you have a much higher groundwater level. And therefore, it's because of the high concentration of groundwater recharge, you get more landslides in that particular location. So here's just a zoom-in look of the landslides in section 2. We're going to be focusing on today in this talk, it's going to be the DC number 2 and DC number 3 flow slides. And here, moving on, I want to show you a little bit of before and after flow slides for DC number 2 landslides. So in general, we define flow slide as a failure surface entirely developed within the loess layer, and it's large to medium scale failure with rapid movement, with long runout and liquefied flow behavior. So the retrogressive here really means just repeated slope failure at the same location. So the new landslide develops behind the scarp of the previous landslide. And you can see from these pre and after images here, here is in 2015, you have the DC number 2 landslide site, and you have 3 months later, you see the failure of the flow slide. So back in January 2015, when we first got deployed to that location, we didn't really have much of resource in the instrumentations with us. So we decided that to a very rudimentary way, we placed the markers on the ground in the crown area of the landslide, and then we start measuring the relative displacement of those of the markers. And what we find here within the 3 months period of measuring, what we find here, the gradual deformation can be seen from the crown area, but this is not a sufficient indication that a flow slide would occur. This also highlights this rapid movement, just 3 days between the failure and the last record of the marker displacement. And something definitely extraordinary happened within that 3 days period of time. So so you see the rapid deformation of the of the slope, and also here go the flow slide. And here I just want to show you a bit more about this sequence of images here. This is, excuse me, from the Google Earth. You see the 2004, and you see this previous landslide scarp. And 8 years later, when the human activities begins to intensify in that region, you see the house is being located here. And you see this white color here on the surface of the slope. That's the salt coating. And that's the interparticle bonds that washed out by the irrigation or by the groundwater when they seepage through the slope, and then the salt get deposited. And a few months later, you see this first landslide occurred, and a few months later followed by the flow slide that developed at the same scarp, at least the location of the same scarp. And here on your right, you see a more recent images where you have this failure that occurred in DC number 2 and DC number 3. Here you see this merging apparent spring line. That's the area of the groundwater seepage. And here, a year later, you see the propagation of the groundwater seepage, and you see the white coating being deposited on the surface of the slope. And here you see some localized failure behind the scarp. And 9 months later, from the last image taken, and then you see this development of flow slide in the DC number 3 location. Now, at this point, we can pretty much convince ourselves that this has something to do with groundwater recharge. Groundwater might be a key player for the development of flow slide. And at this point, we can see this flow instability or severe, intense strain softening that occurred in these areas when the loss is being experienced with such a high groundwater recharge. And now let's move on to the laboratory settings and look at how this flow instability or the mechanical behavior of loss depending on the structure of the material. So in general, we defined flow liquefaction or static liquefaction as a sudden loss of strength with the development of larger strains and accompanied by increasing pore pressure under monotonic loading, resulting in flow failure. So given by Robertson's nice summary of the common soil and instability features of flow liquefactions, you can see the materials tend to be geologically young, and they are low plastic to non-plastic, and then they're very loose, very contractive. They have low effective stress, and the most importantly, this minor disturbance can trigger a massive, quick liquefied flow behavior of the slope. Here we gonna be using a very conventional triaxial test. Results here are probably not very familiar with you. So the effect of structure really means, so well, first the structure here really means the interparticle bonds and also the fabric. Fabric is the arrangement of particles, and the bonds is any interactive, interparticle force that connects the particles. So the effect of structure, by comparing them, we actually compare the intact loess, which is the natural structure, and also the reconstituted loess, that presumably is going to be the structured state of this intact loess. So by comparing them, we can get a sense of this effect of structure. And here we can see from this conventional triaxial test, you can see the results of the undrained shearing, and you can see a very intense strain softening and contractive behavior in these images. And you can see this development of the high pore pressure and also this quick reduction of the post-peak strength for both intact and reconstituted states. And here you can see these images here on your right. If this image was from the previous slide, you can see the pre-test image, and you can see this post-flow liquefaction image. We can see the common porous structure disappeared in those SEM images. Now moving on to the critical state lines. If you look at it, so here I want to just recap. So for the intact and versus reconstituted, we have the void ratio that for the intact is around a much smaller region, and for the reconstituted, we tend to build a reconstituted state with a little bit wider region of void ratio, initial void ratio. So no liquefaction has been observed, which means the true liquefaction here, we're talking about the Q and the pre-prime that approaches very close to zero. But we did find the offset in the pair of critical state lines for intact and reconstituted states. For at least the silty loess, it's nonlinear, and for clayey loess is much more linear, appears to be. And also, but still there's an offset between the intact and reconstituted, likely due to the effect of structure. And also we observed a state-dependent strain softening. And what we can see here is the interesting results from here is depending on the stress level, you have a very robust compressive resistance because of the structure of the intact loess. So when you compress it, it will have a high resistance to compression. But for reconstituted state, the structure doesn't really exist. The cementation doesn't really exist in that sense in terms of compressive resistance. So we will have a higher state parameter for the intact loess at the beginning of shearing, and then causing a structure that is much stronger and more susceptible to static liquefaction. So here, just want to quick talk about this the effect of grading on the instability, on the flow instability. So here we use the sandy loess, and we use the sandy loess, the reconstituted state, and we mixed it with different fines content. And what we find here is you can see a parallel shift of the critical state lines as you're moving downwards, by increasing the fines content, and start to rotate as you continue to increase the fines content. But if you use an equivalent interfines void ratio, which characterize the fine grain dominate to coarse grain dominated soil mix, that you can sort of determine that you can connect the straight line for all the fines content between group 2 and group 4, between group 1 and group 4. And that means, so you have a threshold fines content around 55%. And as you continue to increase by comparing different types of loess, clay and silty, and they will find that the rotating behavior sort of appears again in the critical state lines in this equivalent interfine void ratio. And that means at that point, as you continue to increase fines content above 90%, you are hitting the sort of the limiting fines content. Very likely that's going to be around 90%. And that shows the reduction of the effective, that causes the coarse grains to be fully dispersed, and the fines is in control of the shearing behavior. And also, if you put an intact soil here, that gives you the reduction of the stress, the effective of stress, as you are increasing the stress level. And because this, you can see this sort of the convergent trend for the intact to the reconstituted state. So I'm just going to quickly talk about this one. So if you can use a modified state parameter to capture the flow behavior. So by proposing a criteria for the modified state parameter, you can actually find that it gives you very well where those modified state parameters sitting in this chart. That gives you a prediction, sort of where how intense the flow behavior is going to be, whether it's going to be a flow instability or it's going to be dilative non-flow behavior. So if you look at around 100 kilopascal, you can see these different images. You can see, for example, this triangle here, and that gives you a non-flow behavior because it's more dilative than contractive. And here you can see a very not intense, but still a contractive behavior. So you see the limited flow instability here as represented by this triangle. And the problem with comparing the intact and the reconstituted sample is that in the laboratory setting is extremely difficult, if not practically impossible at all, to compare them at the same state parameter. So we need a constitutive understanding how the effect of structure can actually affect the development or the onset of a flow liquefaction. So we use the NorSand model here, and then we calibrate the model separately for both intact and reconstituted soils. And we can see here that in the calibration, we find that so the elastic stiffness and the strain hardening parameters in the NorSand model actually can change the pore pressure development rather significantly, because the larger elastic and strains, plastic strains are developed to compensate for the shear-induced contraction on this constant volume, as you can see here. But the NorSand, bear in mind, the NorSand model is a constitutive model for particular material, so they don't really consider the cementation. So we have to manually introduce a OCR of 1.6 to reflect this cementation or structure for the intact loss. So after the calibration, we can now compare more directly the mechanical behavior of intact and reconstituted loss at the same state parameter. And what we find here at the low stress level, at least, that a larger strain that can develop for both intact and reconstituted samples. And what we find here, there is a severe reduction in the post-peak strength. And so the peak for the intact loss. And in fact, the post-peak strength for the intact sample is about half of the reconstituted sample, all other facts being equal. And that point, so you see we have the rapid reduction of stress and the development of excess pore-water pressure. That leads to a larger strain development to maintain the equilibrium, as shear strength required is greater than that can be mobilized in the soil. So a quick recap here, basically the laboratory results and the constitutive modeling tell us is that the effect of structure can either facilitate or impede the onset of a flow instability of loess, depending on the state of the soil. And the structure of loess tend to facilitate the development of flow liquefaction or flow instability at a low stress level with a peak post strength of intact loss significantly lower than the reconstituted state. Now we want to be moving on and talk about a little bit about the physical modeling. So in the field, as you can see from this image on your left, so if you rope down from the top of the crown to the bottom and to the top of the displaced material, you can actually take samples 1 meter at interval behind the scalp and also from the flanks of the landslide. And you can find that the moisture content of those samples have a significant difference depending on the location. As you can see, the groundwater level behind the scump is much higher than the flanks. So you have a hydraulic gradient essentially here on that location. And what happens here, this, in this conceptual model that we want to be sharing with you, this, for the flow slides, we first have cracks because of this saturated basal zone of the loess. You can have tensile cracks developing on the cracks on the crown area of a landslide or the free face in general. And what happens is, as this deformation continues, you will first experience a localized failure due to axial strain development, continues to development at a more gradual rate. So this, but what happens is this localized drained failure with a small scale, as you can see in the image in the middle. The two things will happen when the small failure occurs. First, it will introduce a new free surface, which in turn introduces a hydraulic gradient and causes the groundwater to converge to that free surface. And also, the displaced material of that small failure is likely to cover and impede the surface discharge point, causing a drained loading to undrained loading transition. And if that occurs, that is likely to cause this undrained shearing and causes a second subsequent flow slide to occur. And in the conceptual sense, this is appears not moving. Okay. Yeah. Now this let's look at this particular conceptual. Now, when you have when you sharing the material first along the drained loading path, and then you suddenly switch the valve in the laboratory setting, you switch the valve and tends to undrained, you will expect a quick reduction of the strength. And depending on how much you have been sharing along the drained versus undrained loading path, when you shut off the valve, that will cause a much different behavior as in the material, but regardlessly, you will see strength reduction. And here, if you're standing in this location here, and you are likely to see this. Let me show this image. Can I, oops. Can I show the video? Yeah, now I can show the video. So when you're standing at that slope surface, you can see if you stamp on the sample, you can actually see this, this is happening. So that's how saturated this location is. And so from this image, you can see very complicated and sophisticated in situ dynamic loading test. This is really everywhere. This is not just at one particular location. This is, you can see a lot of this floating loess on this on that location. Now, for the centrifuge modeling, this is what we want to use for the to study the slope deformation process and also the failure mechanism of loess flow slide. So in this model, we use the reconstituted silty loess. And the reason we didn't use intact is because it's, well, first, if you want to place sensors inside your slope, you have to essentially destroy your sample. And at that point, you are creating a model slope that is not intact and that is not reconstituted. So using the reconstituted sample gives us much more flexibility in terms of sensor deployment and also just making the model. It makes it much easier to do that. So the goal here is really to study the conceptual failure process. And then first, what we find in the field that there's a change in the slope geometry, because from the previous first drain failure. So when you change the slope geometry, especially along the toe area, causing the development of a pore pressure to change, and that will give you, likely that will give you the base of the slope that is more prone to liquefaction with the continued increase of pore water pressure. And also at that point, if you have a groundwater level increase or just a minor disturbance, we think that can further compromise the stability at the base and also basically leads to the flow liquefaction and the flow slide. So as you can see, this is the 3D scan. The 3D scan of the surface of the model slope, and we can see the rough geometry of that, and then we place the 8 sensors inside. You can see from this layout, from this high-speed camera sitting right in front of the model box here, and you can see the sensors inside. You can see this a coupled sensor of pore water transducers and also total pressure sensor located just in front of the slope to confirming the development of flow slides or development of any movement in general. So, and also here is the water reservoir that basically gives us the reservoir of water in the back of the slope that simulates in principle the increase of the groundwater level and the propagation of the phreatic surface inside the slope due to in the field irrigation. So in this classic FEM model, what we can see here is that if your slope stability is at a unity at that point, if you have a induced, manually or artificially induced a change in the slope geometry, you are likely to further compromise the flow instability from the factor of safety sense. So here is the slope model. And you can see here is the propagation. Of course, this is the image at the very beginning of the test, but you can see the yellow line indicates the propagation of the phreatic surface along inside the slope, as you can see from the side of this high-speed camera. And here you can, let's see, we can look at this. I want to show you this. Oops. Back, nope. How do I? Want to show the propagation of the slope. And it's not playing. Okay, well, so basically what happened is a couple of things that happened here. So when you have the phreatic surface propagating, and here, well, first, during the initial acceleration, you see this surface subsidence a little bit. And as you have the groundwater start to increase, groundwater levels start to increase inside your slope, and you have the phreatic surface propagating and reaching the toe at about t at 80 minutes. Since the beginning of the test, and that's the end of the pre-failure saturation process. And when that happens, after that, we registered a slow-moving slip for the entire slope to moving very slowly, very gradually, and by changing the slope geometry, and also especially making the slope becomes more gentle, and the slope angle becomes smaller here, and then the flow slide, which appears to be a flow slide that initiated around 130 minutes into the test and caused the more diffuse failure. And if I can show you this propagation of the phreatic surface, then that would be great. But for some reason, I can't really show it at the moment. Yeah, I'll just go ahead and give you the figures of the sensor readings. So here you can see this is at the beginning of the start to see the flow slide initiation right before that, and also this is right after the flow slide initiation. So sorry, after the flow slide occurred. So so a few things that you can get from this reading of the sensors reading. So here. After the initial slow-moving slips, And you see, we increase the influx of groundwater. So we increase the groundwater level. We manually introduce more water into the reservoir and introduce and causes the pore pressure to increase. At that point, we maintain about the same acceleration. And you can see the rapid response of the pore-water transducers. And you can see number 3 here, that's located around near the toe of the slope. And you can see if you zoom in this area, the flow slide, the red zone here, and we move here a little bit, and you can see this really in the center. And this is really showing the PPT3, and the PPT3 is increasing, but at the same time, this total pressure of that at the same location is decreasing a little bit. And then if you compare the ratio between the total stress and, well, the pore pressure and the total stress, you can actually see that ratio is exceeding unity. And that means this compounding effect of pore water pressure increase and the confining stress reduction that can trigger, or at least in this case, that provides the favorable condition to trigger static liquefaction in that slope. So we're talking a little bit of more complex dynamics here rather than just the increase of pore pressure. So the pore pressure, and also which you have the change of drainage condition due to the change of the slope geometry, and also the reduction of the confining stress. That combining those 3 reasons or conditions, scenarios, that really gives us the unfavorable condition for the development of flow liquefaction. And that is something not entirely new in terms of how the slope geometry can help the development of flow liquefaction or static liquefaction. So here back in Take's paper 2014, you can see this. We have an infinite slope, you might not cause liquefaction, but if you have introduced a base of slope here at the toe area, you end up having a zone of saturation and end up having an area that is more susceptible to static liquefaction, ergo causing the slope to fail. So in this case, we identified really likely 2 static liquefaction events, as you can see from here and here, that occur during the development of a flow slide. And we observe the deformation process, which in principle agrees with what we find in the field. And especially I want to emphasize a little bit more about the drained to undrained transition that I believe that is the key to the development of a flow slides in Loess. And so if we go back to the NorSand model that we used, if we simulate a scenario that had a initial confining stress of 50 or 100 kPa, and if we shear along the drained loading path and then switch to undrained, which is represented by the K0 here, and the initial shear strength to reflect how much drained loading path has been experienced, we can find that once you go to more than 0.5 for your K0, when you switch to drained, from drained to undrained, you will see a rapid reduction of the strength in your material, and that's for the reconstituted. So this is really extraordinary when it comes to in the field, that if this drained to undrained transition is actually occurring, this is very likely to be a key player for the development of flow slide in the field. So just some thoughts here. So the brittle collapse can occur with any strain softening stress strain relationship. It is not necessarily the collapse of the structure per se that causes the static liquefaction in Loess. And so this is the reconstituted model, as I have emphasized. So as I've mentioned, so for the intact soil, it will be likely to be more favorable and more susceptible to static liquefaction should the condition remain the same. And so the current observation of the external condition is, as I've mentioned, is less favorable to flow liquefaction. And also, I want to emphasize for the Coriolis effect in the centrifuge modeling, the rotation of the centrifuge is actually, the direction of the rotation is actually against the principal direction of the flow slides that we have observed. So if anything, we are creating a condition that is more difficult for flow liquefaction to develop rather than facilitate the development of that landslide. So just got a few more minutes to go. So I just want to, switch gear a little bit here and talk about the visualization of that landslide. So especially under the current environment, when everybody is really sitting at home and looking at the screen, things can be a little bit tedious. And so if I want to show you this study area, which I did in the previous slides, and if you recall, that's the study area of this entire presentation. And if I want to show you the DC number 2 and DC number 3 slides, I can show you, I can point them out here on the map. And if we want to give you a little bit of more interactive environment for those flow slides, I can give you a video. And now you can look at the video and basically says, okay, this is great. So you can follow my recorded video. I'll take you to see at this point, I'm taking you to see the displaced material. And in about a few seconds, I'm going to show you the scarp. And that's pretty much it. And now if at this point, if you want to see the structure that is being damaged by the displaced material, what are you going to do? You have to restart the video and go back, and you have to pause. You have to zoom in, zoom out, which is difficult. You can only do that on the screen level. And here is a bit of fun that I've had last year. So in 2019, back in January, I actually wrote a very small AR enhanced visualization program, which is open sourced. And you can actually place your landslides point cloud into that code. You can basically see the landslide on this marker. So if you take your iPhone out, if you have an iPhone or smartphone, if you have a smartphone with you, you basically take the camera out and scan the QR code. And this QR code will take you to this URL below. And this is the URL. And if you open that URL, if you have access to your camera, if you place the markers within the camera, then you can see this landslide. And when you see the landslide here, and that gives you a more interactive environment to go around and explore what you can see from the features of that landslide. And that is, I find, particularly helpful, especially under the current education environment. We can come back to that a little bit later if you have questions, but just a quick concluding remarks here. So in this talk, we mentioned that for the landslide classification, especially the loss is a little bit undervalued in that classification system. And from the 2014 classification system, you don't really see a loss flow slide or loss landslide per se anywhere in an updated system. It's actually all loss related landslides being lumped into earth flows in that category. And so the structure can facilitate or impede the onset of flow liquefaction. And we see a pair of critical state lines for silty loess and for clayey loess. And so from a constitutive understanding, the effect of structure can facilitate the flow instability at low stress level. And we can use a modified state parameter to better characterize and predict the flow behavior. And also from the physical modeling point of view, we find that the change of slope geometry and drainage condition are essential to the development of flow slides in loess, and also the compounding effect of excess pore-water pressure and the confining stress reduction that is key to the flow liquefaction in at least the reconstituted loss in our model. And the AR enhanced data visualization can really help us to better share information for our landslide. And that's the end of the presentation. Thank you. And
so
I'll
thank
go
you.
ahead and stop sharing the screen.
Thank you so much for your presentation, Dr. Liu. Nice work, and we're happy to see the whole picture of your research work. I'm going to be the moderator for the Q&A session, and I'm wondering, like, if anyone has questions. Now I can see there's one question in the chat.
Okay.
So the failure process you described in loss, where there is a drain type failure followed by an undrained failure, seems very similar to the process seen in quick clays. What would you say are the primary differences between these two mechanisms?
Yeah, so for the quick clay, I hesitated a little bit to directly compare Loess to quick clay because they are still two different types of material. So the structure of Loess, the key for the Loess is not just about the cementation. It's also the open and porous fabric that that comes with the particle rearrangement. So when you have a saturated Loess, it doesn't not necessarily has the huge difference in terms of strength as compared to saturated and disturbed quick clay. So when you have a saturated Loess and a disturbed Loess, you can see different strength, but I don't think the strength is going to be that different as compared to what we see in quick clays. But nonetheless, this similarity can emerge from the mechanism formed between Loess and quick clay in general, and especially when you have this severe strain softening experience during the shearing, especially first along the drained and then switch to undrained. But I personally haven't really done any triaxial test on drained to undrained transition shearing. My study was for that particular bit, it was centrifuge modeling and the field investigation.
Thank you, Dr. Liu, for the explanation. And I think Dr. Martin has the same questions. And
yeah.
Now Kevin asked another one. How do you end up choosing an OCR value of 1.6 to model the cementation of the Loess? What was it done through perforating or different method? Yeah, so
as I've mentioned, that the NorSand model it does not really consider the cementation is designed for particular material. So the OCR of 1.6 is really a value that I came up with during the curve fitting for the calibration process.
Thank you. I don't think there's anything else coming up right now.
Yeah. Hi, Dr. Liu. I have one question.
Yep.
Yeah. Hi, Dr. Liu. I actually PhD from UA, and now I just left UA this year. I have one question for the study, because mostly like for Loess, this area, there are a lot of guys working on this area, like some professor from Lanzhou University and also from China University that are working on the insulation of the landslides. So, but the most key point in this area is to control the landslide and to make sure the locals can survive in this area. So my question is, based on your study, any suggestion for such landslide except the control the irrigation of this area? So because now they have some procedures or some approach to control the irrigation, and they think that can control the movement of landslide or the occurrence of the landslide. Except this approach, do you have any suggestions? Because we are engineers, so we want to serve the locals, right? So what's your suggestion for locals based on study?
Well, so as you have mentioned, I think this, irrigation is the key that causes the landslide, and fundamental level that is perhaps the best solution is to, I'm not suggesting to stop irrigation entirely, but I think through better water resource management and the reduction of the irrigation intensity will be a very good starting point. And we've seen a very clear tendency of landslide reduction by introducing the irrigation regulation in this study area, actually. So since the summer 2019, I think, and also until last month, which is about a year already into this irrigation regulation program that are happening at the local government level, that they are basically reducing the irrigation intensity by helping the locals to basically grow other types of crops rather than vegetables or wheat. By doing that, they reduce the irrigation intensity, and by reducing the irrigation intensity, they better mitigated the occurrence. They reduced the number of landslide occurrences in that study area. So at this point, I think for the locals and for the residents there, for the community, I think the best way to do is to somehow to control the irrigation and also better manage what types of crop fields and that you choose to grow on the surface of the terrace. Other than that, I mean, there are different mechanisms. I've seen very recent papers on different mechanisms to better mitigate it from the soil point. But I still want to emphasize that by the end of the day, the problem is actually water rather than the soil itself. The soil here is fine. I mean, loess is a fantastic material for both research and agriculture, but water is the key here.
And sorry, I have one more follow-up question. So there's another one about the salt inside the Loess in this area. Have you pay attention to the salt in the soil in this area? Because we can see some salt from this area, from the the leakage of the water below the hill.
Yep.
So do you pay attention to such effect?
Yeah, salt is the main cementation agent we see there, and that's why what I've shown in the field image. A lot of the priority to the failure of a landslide or a flow slide, and you can see a lot of the white salt coating being deposited on the slope surface, and I think that's a very good indicator of the deformation of the slope, and if not the development of a landslide.
Okay, thank you. Yeah.
All right, I think it should be better to adopt this seminar on time. So now we're allowed to have one question, and this one is going to be from Natalia, and she's asking which software you use to model the landslides.
Oh, so basically the NorSand model is a nice and neat model that can be implemented in MATLAB or in Excel if you want to. It's not computationally expensive at all.
Okay, thank you. That's a simple answer. And so for the future, like in order to keep the seminar under control, like to keep it under the right time. So I will suggest everyone to post your questions into the chat. So we will have repeat your questions and choose the one for the presenter to answer. And now I think there's still some questions from students, but I would suggest you to follow up with Dr. Liu by email, and the email will be provided through the group chat. And with that, I would like to appreciate the efforts and your time from all of you. And we're looking forward to the future collaboration with Dr. Liu in the group. And there will also be some events coming up in the future. We will keep all the students and the staff updated.